So we're going to look at solving absolute value equations and inequalities. We're going to focus on doing this graphically, not algebraically. So now that we know how to graph these absolute value functions, how can we use these graphs to find solutions? So let's say I have this absolute value function f of x that's in purple here, and I want to solve this equation. I want to see where does this function equal 3. So what we can do is draw the constant function of 3, which is this horizontal line right here across y equals 3. And if we're solving, it's kind of like, in fact it's not kind of like, it's exactly like solving a system of equations. We have one equation being graphed, we have our second equation being graphed, and if we want to see where they're equal to each other, it's the intersection points. So when we solve, we typically list the x values for where the solutions are, and what we're seeing is that there's two solutions. One is at x equals -1, and the other is at x equals +5. So solving an equation, what we're going to do is graph both sides of the equation and see where they intersect with each other. Now solving an inequality, we're doing something we're kind of mixing together when we talked about graphing inequalities, that idea, along with this solving systems of equations. So if I want to see where my function is less than 3, what I'm going to focus on is where's this region where everything is less than 3, and that's going to be below the constant term. Below that horizontal line is what we would graph if I just wanted to see where is less than 3. However, we're being specific about our function here. So what I want to do is see where does my function intersect with that region of the graph. So what I would see is that it is this portion of the graph that is underneath that y equals 3. It's this portion of the graph where I'm seeing my solutions. So I'm seeing everything from -1 to +5. So what I'm going to end up with here is an interval as a solution. And then what I just want to see is that we're not including y equals 3. We're being strictly less than 3. So what we're going to have are these open circles where they intersect, because we want to get infinitely close to those points, but we can't actually equal those points. So for my solution set, how I'm going to express this is in terms of x. We can have x from -1 but not including -1, all the way up to x equals +5 but not including +5. So we're going to have the interval -1 to +5. And we would use parentheses because we're not including those endpoints. Now let's say I wanted to look at the function being larger than 3. So again, I want to focus on where is larger than 3, and that's everything up above the horizontal line. So I'd have this shaded region, but I want to see where does that intersect with my function. So what I would have is with my function, these upper areas. So I have this line that's going to continue on forever, and I have this line that's going to continue on forever. And again, because we don't have equality there, it's just strictly more than, we're going to have these open circles at -1 and +5 because we don't want to actually include those points. So what we'll have for our region where this holds true is starting at -1 but not including it, and then everything smaller off to -infinity. And then we'll have starting at 5 but not including 5 and going off to +infinity. So we end up with these two regions that are solutions where our function is larger than 3. So I'm going to have -infinity to -1 with parentheses because I don't want to include that value, union, starting at 5 but not including 5, off to +infinity. Alright, let's look at another example where we're kind of changing some values around and we're using this function negative absolute value of x plus 1 plus 5. So what you can see here is I've input the actual function so we can see it in there, and There are ways of solving this algebraically, but we're just going to focus on the graph. So this first piece here is really the same thing as solving f of x equals 3. This is the same thing as solving f of x is more than or equal to 0. This is the same thing as solving f of x is less than 2. So if the notation seems confusing with having the actual absolute value function in there, you can just substitute it with our function. Or maybe it makes more sense to see the function written out, because then you can see how our graph is coming through. And just a quick little review of our graphing, just to see how this is connecting. So we have this -1 out front, so that's why it's opening, it's opening down. And then you could see this slope of 1 coming through, so that's where we have a -1 coming through there. And then for a corner, we would have -1, 5, and that's where you see -1, 5 for our corner. So that's where you can see the structure of the graph just from the function itself. Okay, if I want to see where this function equals 3, then what I'm going to do is draw a horizontal line at +3. And since it's equals, I just want those intersection points. So we're seeing one intersection point at x equals -3. We're also seeing an intersection point at +1. So x can equal -3 and +1. Alright, for where our function is more than or equal to 0, I'm going to change where my horizontal line is. It's going to be at 0 now, so we're along the x-axis here. And I want to see where is it larger than or equal to 0. So if it helps to think in terms of a shaded region, we're up here, where we have larger values than 0 for the outputs. But I just want where my function is landing. So we're going to be bounded between two values. And then because it's more than or equal to, we want to include the intersection points where they meet. So what we're going to have is starting at -6 and including -6 all the way up to +4 and including +4. So for x, we'll have square bracket so that we're including -6. For square bracket so that we're including +4. Alright, and then our last one here is for less than 2. So what I'm going to do is make my horizontal line at +2. And then I want to see where the function is smaller, so my shaded region would be underneath that line. So I'd have everything down there, but I just want where the function is intersecting with that. So I'm going to have all of these values along that part of our function and this part. And then we're looking for strictly less than, so we're not going to include the intersection points. So what I have is starting at -4 but not including -4, off to -infinity. And then starting at +2 but not including +2, off to +infinity. So I'm going to have -infinity to -4. Union with +2 off to infinity using parentheses because we're not including those endpoints. So that's how we're going to work with solving absolute value functions. Just think about graphically, have your absolute value function, and then where we plug in these constants, draw a constant function for that number, which will be a horizontal line.